2,000 feet below me on this Dorset cliff is British oil. And the purpose of this device is to pump that oil out of the ground. It's sometimes known as a nodding donkey. Sometimes that's called the donkey's head. And it operates, just like the other devices you've just seen, by means of a linkage mechanism. Well, let's see how it works. At the business end here, we have a solid steel rod, which is attached to a plunger under the ground, sliding up and down inside its casing like a large bicycle pump, forcing the oil out of the ground through these pipes and off to storage. Well, that's the output motion of the mechanism, a reciprocating translational motion. But what drives the mechanism? What is the input? At the input end is a continuously rotating crank driven by a small motor. And between the input crank and the output pumping rod is a series of connecting links forming a kinematic chain. Let's examine the individual links in more detail. Starting at the input, the crank, with its huge counterweights for balancing, is in fixed axis rotation about this central drive shaft. In its turn, the crank forms a rotating pair with this coupler link. Let's look at the motion of that coupler link. How would we classify the motion? Well, it's rotating, but not about a fixed axis. In fact, we could think of the motion as being a combination of a fixed axis rotation and a translation. It's in combined motion. The coupler link forms another rotating pair with the beam over the top. And we can get a better view of that connection if we go up top. I think that's far enough. Well, there's the rotating pair connection between the coupler link and this overhead link. As you can see, it's just a massive pin joint. The beam itself is in fixed axis rotation about a fixed pivot at the center. It's oscillating through an angle of about 40 degrees. And it's the rocking motion of this beam which is transmitted through the donkey's head to give the up and down motion of the pumping rod. Well, that's about it. The whole mechanism is designed with one purpose: to convert an input rotation into an output translation. And that's what mechanisms are all about: transforming one motion into another, inputs to outputs.
A bit more down to earth, here are a couple of rather more simple mechanisms. Here's our input, and the output squeezes the sponge. It's an input translation to an output rotation. In this design, both the input and the output are rotations. Actually, these mops are examples of two of the simplest forms of mechanism. But what do we mean by the simplest form? Well, the function of any mechanism is to take an input movement and convert it to an output movement. This can either be continuous, as with the nodding donkey, or intermittent, as with the mops. Now, any motion of a rigid body, no matter how complicated, can always be reduced to a combination of a translation and a rotation. So all linkage mechanisms can be thought of as devices which convert input rotations and translations to output rotations and translations. We'll start by looking at a rotation input to a rotation output. The simplest form of mechanism which does this is called a 4-bar linkage. In this model, here's the rotating input, and this is going to be our output. The simplest way of joining or coupling the two is with a single coupler link. You can see that although both are rotations, the input is continuous, whilst the output oscillates. That's because of the geometry. It's the relative size of the links. So, arrangements of links like this, a 4-bar linkage, form the simplest way of converting an input rotation to an output rotation. It's important that you recognize that there are 4 bars, or links. I think 3 of them are pretty obvious. There's the input crank, the output rocker, and the coupler link. The 4th is not so obvious, but it's just as important. That's the fixed link, which joins these 2 pivot points. It's made up of the baseboard. So, that's one possibility, a 4-bar linkage converting an input rotation to an output rotation. Another possibility is to have an input rotation converted to an output translation. You've seen one example of that with the nodding donkey. But that's not the simplest form. Here's my input rotation, and this time I want to convert that to an output translation here. If I join them with a single coupler link, as before, I'm sure you recognize that as a slider crank mechanism. Again, there are 4 links. The input crank, the coupler link, the slider itself is a link, and as before, the fixed link, which is the baseboard. Of course, the same arrangement can be used the other way round. Many slider cranks are designed to convert an input translation to an output rotation. One example is the mop that we started with. Here's our input translation being converted to an output rotation. This is an example of a slider crank. And the other one, well, here's the input rotation and the output rotation. Here we have the 4 links, 1, 2, 3, and the fixed link, the handle, making up a 4-bar linkage. So, there we have our 2 basic forms of mechanism, the slider crank and the 4-bar linkage.
Well, the floor mop is not exactly what you would call a high-technology application of a linkage mechanism. The most common application of the slider crank linkage is the reciprocating internal combustion engine. Let's look inside in order to see the slider crank mechanism in operation. The motion has been slowed down so that we can see the movement of each of the individual links. The motion comes from the force of the gases pushing down on the piston, which is constrained to slide inside the cylinder in translational motion. The connecting rod transmits this motion to the output rotating crank. So we have a translating motion giving rise to a rotational motion. If we now simplify the schematic diagram further, we can see the line diagram of a slider crank mechanism. Well, this is one of the basic forms of linkage mechanism. Can you see the 4 links? Well, there's the fixed link, 1, the crank, link 2, the connecting rod, link 3, and the piston, link 4. Well, the animated line diagram which you just saw was operating at about 45 RPM. Well, that was all right for our purposes because we were just looking at the motion of the individual links. But the engine itself was operating at around about 2000 RPM. Later on in the course, you'll be looking at the forces generated within individual links of engines running at that kind of speed.
Elsewhere in the car, we have another application of a 4-bar linkage. This is a model of one design of windscreen wiper mechanism. Here you can see the crank, the coupler, the rocker, and of course the fourth link would be the body of the car. So, there are the 4 links making up another crank rocker. But the crank rocker is only one possible configuration of a 4-bar linkage. To help us understand better what the other possibilities are, let's take a look at the line diagram. There are 4 links with rotating pair connections. The behavior of this assembly will depend on which link is chosen as the fixed link. With link 1 fixed, for example, we get a crank rocker of the type used in the windscreen wiper. Link 2 is the rocker, link 3 the coupler, and 4 is the crank. With link 2 as the fixed link, the 4-bar linkage becomes a double rocker mechanism. And when link 4 is the fixed link, a double crank is the result. So, in which the 4-bar linkage operates depends on which of the links forms the fixed.
Now, all those different kinds of behavior were produced from the same 4-bar linkage, simply by considering different links in the chain as the fixed link. We can apply the same process to the slider crank linkage, which you've met already in this form, the piston engine. You'll remember that the fixed link in this case is the engine block itself, which guides the motion of the piston and the crank. On the line diagram of the engine, we've labeled this fixed link, link 1. Now, if we fix the link that was previously the crank, link 2, we get an inversion of the slider crank. Link 1 now rotates continuously. In fact, this inversion is part of a Whitworth quick return mechanism, similar to the one you've analyzed in the text. And fixing link 3, we get another inversion, an oscillating cylinder mechanism. So much for inversions. Up to now, we've concentrated principally on linkage mechanisms in their simplest forms, with a single input and a single output, and 4 links in the chain. But many mechanisms have more than 4 links.
The JCB digger, or to give it its correct name, the JCB backhoe loader. It's a very versatile machine, which is why it's covered in mechanisms to do all sorts of different jobs. We're going to look at the motion of the front shovel. So as the machine operates, we'd like you to study the motion and see if you can identify the mechanism that produces it.
Notice as the main arm moves, the shovel remains level. This self-leveling of the shovel is controlled automatically by the mechanism.
Well, as you can imagine, it was quite an interesting problem for the design engineers to design a mechanism to produce the motion. The shovel is controlled by this mechanism here, which looks a lot more complicated than the simple 4-bar chains we've looked at so far. But in fact, it's a series of 4-bar chains connected together. So the output of one is the input of the next. This is the first one. Its fixed link is the main frame of the machine here. And the main arm is the input crank, which is in fixed axis rotation about here. This is the rocker, also in fixed axis rotation about here. And notice that it's the coupler that provides the output. Designing it this way, with the rocker well down here, gives the operator a clear view of the shovel. Now coming on to the second 4-bar, this one, its fixed link is the main arm. And this coupler, extended, becomes the input crank. So we have input crank, second coupler, and the output rocker. This is the third 4-bar chain. This rocker is now the input crank, coupler, output rocker, which is the shovel itself. So the self-leveling effect of the shovel is controlled entirely automatically by this series of 4-bar chains.
Look at the 3 4-bar chains. Notice how their geometry changes to keep the shovel level.
Notice that there's a separate operation. The middle coupler can be extended hydraulically to provide another input to the third 4-bar chain to tip the shovel right over. Well, I hope you can see that it was quite easy to break down what looked like a complicated mechanism into a series of 3 4-bar chains. Of course, the clever bit was to get the linkage dimensions and the geometry exactly right.
JCB's designers use computer-aided design techniques. With these, they can design and predict all sorts of mechanism behaviour. Even so, our machine's mechanism was designed using precisely the same techniques you'll be using, constructing position diagrams and so on. The computer merely allows the designer to do this much more quickly and try out alternative ideas.
So even what looks like a complicated mechanism can be broken down into a series of simple chains of 4 links. We can analyze the nodding donkey in exactly the same way, looking for those simpler forms. We'll start by looking at its schematic diagram. We've already seen it's a rotation in and a translation out. What's more, the linkage system between the input and output is made up of 2 4-link chains. The left-hand side is a 4-bar linkage. The fixed link, 1. The crank, link 2. The coupler, link 3. And the rocker, link 4. So we have a crank-rocker mechanism for the left-hand side. The rocking output from the left-hand side becomes the input link for the motion of the right-hand side. So on the right-hand side, we have a form of slider crank. The whole mechanism, then, is a combination of 2 4-link chains in series. Well, there we are. We've looked at mechanisms in terms of their function as motion converters and illustrated the behavior of 2 basic forms, the 4-bar linkage and the slider crank linkage. We've also seen that more complex mechanisms can be thought of in terms of these basic forms. And that's really the method for sorting out how mechanisms work. Identifying the input and output motions and looking for the simple chains of 4 links, which are the basic building blocks of all planar linkage mechanisms.